What really is space? That vast black stretch we see when we look up at the night sky. To most people, it seems like nothing at all. A giant empty place where stars shine, planets move, and maybe socks disappear. But the truth is, space is far from empty. It's active, full of mysteries, and one of the most fascinating parts of the universe. For a long time, people thought of space as just a stage flat, fixed and unchanging. Sir Isaac Newton described it as an absolute grid, where time ticked the same for everyone, and objects simply moved around. Then came Albert Einstein, who turned that idea upside down. He showed that space and time are connected into one thing: space-time. And space-time is flexible. It bends, stretches, and curves, depending on the mass and energy within it. Think of how Earth curves space-time. You don't fall toward Earth because it's pulling like a magnet, but because the ground beneath us is curved space and we're sliding into it. That's gravity in Einstein's view. But what about the spaces between stars? Are they really empty? Not at all. Thanks to quantum physics, we know that even empty space is alive with invisible fields. Every particle, like electrons and photons, comes from its own field. And even when no particles are around, these fields flicker with energy. Tiny virtual particles pop in and out of existence for the briefest moments. This restless energy is called vacuum energy, and it's part of why scientists believe the universe keeps expanding faster and faster. It has structure, movement, and energy. It can stretch, ripple, and even expand. The vast emptiness between galaxies still holds. A faint warmth, just a few degrees above absolute zero left over from the Big Bang, and that expansion brings us to the observable universe. Imagine standing on a hill at night, looking out as far as you can see. You'd think the farthest light we could detect should be 13.8 billion light-years away, since that's the age of the universe. But because space itself has been stretching, the actual edge we can see is much farther, about 46.5 billion light-years in every direction. That makes the observable universe nearly 93 billion light-years across. So, when we ask, what is space? The answer isn't emptiness. It's a living fabric that holds everything together: atoms, stars, galaxies, and us. Space isn't just where things happen. Space is part of what happens. On the largest scale, we reach the idea of the cosmic horizon. It isn't a wall at the edge of the universe. You wouldn't crash into it with a spaceship. Instead, it's more like a limit to what information can reach us. Beyond this horizon, light from distant regions simply hasn't had enough time to arrive since the Big Bang. It's like standing in a fog. You can only see what has already made its way to you. This horizon marks the edge of our observable universe, and it keeps changing. Over time, light from farther regions will reach us, so our view slowly expands. But because the universe is stretching faster and faster, some galaxies are moving away so quickly that their light will never get here, not even after trillions of years. They aren't breaking the speed of light. Space itself is expanding too fast. Here's something beautiful. Every star, every galaxy, every patch of light we see is within our observable bubble. But there is almost certainly far more beyond it, possibly infinite, that we'll never be able to detect. And each location in the cosmos has its own observable universe. If you were standing on a galaxy 10 billion light-years away, your view would overlap ours, but also reveal areas we'll never see. In short, the observable universe is just our slice of the whole. That slice is still huge, around 2 trillion galaxies, each with millions or trillions of stars. The light from many of them has been traveling for billions of years before finally reaching your eyes or a telescope. Some of that light left its galaxy long before Earth even existed. Observing it is like looking through a time capsule. This brings us to the idea of look-back time. The galaxy is 8 billion light-years away. We are seeing it as it was 8 billion years ago. We don't see galaxies as they are now, but as they were when their light began its journey. Some may no longer exist in the same form. They could have merged, run out of fuel, or moved beyond our reach. The universe we see is, in many ways, a fossil record written in light. Light also changes on its journey. Space expands. Wavelengths stretch. shifting light toward the red end of the spectrum. This is called redshift. The farther away a galaxy is, the more its light is redshifted. By measuring this, astronomers can learn how distant it is and how long its light has been traveling. High redshift means we're peering deeper into the early universe. These signals reveal the history of cosmic expansion and even give clues about mysterious forces like dark energy. And then there are telescopes, are true time machines. A small backyard telescope might show you Jupiter's clouds as they were 40 minutes ago. A larger one can capture galaxies as they appeared hundreds of millions of years in the past. And great observatories like Hubble and James Webb allow us to look back billions of years, almost to the dawn of the cosmos. Modern telescopes can see so far that they capture the faint glow of the first galaxies, which began forming only a few 100 million years after the Big Bang. To study the universe's future, we first look deep into its past because light takes time to travel. The farther it comes from, the older the story it carries. So, in a sense, the universe we see is always a little outdated, yet that delay is a gift. It lets us view different stages of cosmic history all at once, like scattered chapters of the same book. When we gaze at nearby galaxies, we see them as they were not long ago. When we look farther, we're witnessing light that began billions of years ago, when stars were just starting to form. In every direction, the night sky becomes a museum of light, with photons traveling immense distances to bring us messages from the past. Each star you see is not as it is now, but as it once was, sometimes before Earth had trees, air, or even life. This is why astronomers speak of cosmic horizons. They set the boundaries of our observable universe. The first is the particle horizon, the maximum distance light has traveled since the universe began 13.8 billion years ago, because space has been expanding the entire time. Its distance is about 46 billion light-years in every direction. It's making the observable universe roughly 93 billion light-years across. It isn't a wall, but a limit of visibility signals beyond it simply haven't reached us yet. The second is the event horizon. Unlike the particle horizon, this marks regions whose light will never reach us, no matter how long we wait. Today, this boundary is thought to be around 16 billion light-years away. Galaxies beyond this point are receding faster than light because space itself is stretching. We can see some of them now, but any new light they emit will never arrive. Over time, more galaxies will drift beyond reach, disappearing from view forever. Lastly, there's the broader cosmological horizon, a term often used to describe all such observational limits. It expands as time goes on, allowing us to see more ancient light. But because of dark energy and accelerating expansion, the event horizon ensures we'll also lose sight of countless galaxies. These limits remind us that while the universe may be endless, our view of it is not. Our perspective is shaped by time, distance, and the physics of space-time. There will always be regions beyond our reach, not hidden by barriers, but beyond the possibility of information ever arriving. And yet, within these boundaries, we've uncovered extraordinary things. Maps of galaxies, the glow of ancient radiation, and fingerprints of the Big Bang itself. Horizons don't end our curiosity, they guide it. With each discovery, the fog of the unknown lifts a little more, even as some regions remain forever silent. Still, here we are in a small world, watching photons that left billions of years ago, reading their stories and wondering what lies beyond. Even if we can't see it all, the attempt itself connects us to the universe. Not too long ago, many believed the cosmos was calm and unchanging. But in the early 20th century, Edwin Hubble made a discovery that proved the universe is anything but still. When Edwin Hubble studied distant galaxies, he noticed something remarkable. Their light was always redshifted. This showed that galaxies were moving away, and the farther they were, the faster they receded. It wasn't a random event. It revealed a law of nature. Space itself is expanding. This doesn't mean galaxies are flying like race cars through space. Instead, space is stretching, carrying galaxies along with it. Picture dough rising with raisins inside. The raisins aren't moving on their own. The dough between them is growing. In the same way, no galaxy is the center. From anywhere in the universe, everything else appears to be moving away. This idea was so radical that even Albert Einstein had to rethink his equations. He had once added a cosmological constant to keep the universe static. When Hubble's discovery proved expansion was real, Einstein admitted it was his greatest mistake. Ironically, the same concept later returned as a way to explain dark energy. Hubble's findings also allowed scientists to rewind the clock. If galaxies are moving apart today, they must have been closer long ago. This led to the idea of a hot, dense beginning, the Big Bang. It wasn't an explosion at a single point, but the rapid swelling of space everywhere at once. Nearly 14 billion years later, expansion continues, and light keeps stretching as it travels. Expansion, though, doesn't pull everything apart. Gravity holds galaxies, stars, and even your morning coffee in place. The Milky Way isn't expanding. Your neighborhood isn't expanding. But on the largest scales, the universe grows, and, in the late 1990s, scientists discovered it's doing so faster than expected. Something unseen, now called dark energy, is driving this acceleration. It may be a property of space itself, but whatever it is, it dominates the universe today. This raises another puzzle. Einstein's relativity sets a hard limit. Nothing with mass can travel faster than light, about 299 million meters per second. Yet astronomers see galaxies that appear to move away faster than this. Are the laws of physics broken? No, the trick is that galaxies aren't racing through space. Instead, space itself is stretching so quickly that the distance between us grows faster than light could close the gap. A simple way to picture this is a treadmill that speeds up. No matter how fast you walk toward someone, the belt pulls you back faster. In the cosmos, light itself, as the walker in space, is the moving treadmill. Some regions are expanding so quickly that light can never reach us from them. This idea connects to cosmic inflation, a burst of expansion right after the Big Bang. In less than a trillionth of a second, the universe ballooned from smaller than a proton to something the size of a grapefruit or larger. Inflation smoothed the universe and explains why it looks so uniform today. And just like then, galaxies far away are still being carried beyond our reach. Some of these galaxies now drift away faster than light, not because they're moving too fast, but because the road between us is stretching too quickly. That means parts of the universe are forever beyond sight. Even if they send out new light today, it will never arrive. In the end, expansion isn't about galaxies racing into empty space, about the fabric of reality itself stretching. What began as a dense, unified start has unfolded into stars, galaxies, and life, and continues to spread outward. The universe grows quietly but steadily, and we are part of that story, living on a small planet bathed in ancient light as space around us keeps expanding. When astronomers say some galaxies are moving away faster than light, they don't mean physics is being broken. What's really happening is that space itself is stretching so quickly that the distance between us and those galaxies grows faster than light can cross it. The galaxies aren't racing through space. Space is carrying them away. Here is the twist. We can still see some of these galaxies, because the light they gave off long ago is still reaching us. But the light they give off now is already beyond our reach. It will never arrive, no matter how long we wait. It's like watching a car disappear around a corner. You see the glow of its taillights for a while, but the car itself is gone. That means much of the universe is slipping out of view. There are stars, galaxies, and whole regions we'll never know about. Not because we didn't look hard enough, but because the universe itself is pulling the curtain closed. Yet what we can see is still extraordinary. Billions of light years in every direction. The birth of galaxies and even the faint glow left from the Big Bang itself fall from a small planet circling an ordinary star. So what does the universe actually look like? We tend to imagine it as a giant box with edges, but the real shape of space is more subtle. Space can be flat, closed, or open, and each shape has different rules. A flat universe is like an infinite sheet. Lines stay parallel, triangles add up to 180, and if you keep traveling in one direction, you'll never loop back. A closed universe curves like a sphere. If you traveled straight long enough, you'd eventually return to where you started. Just as walking around Earth brings you back home, an open universe bends outward like a saddle. Here, lines drift apart, triangles add up to less than 180. And if you set off straight ahead, you'd never circle back, you'd drift further and further into endless space. Which version do we live in? Depends on how much matter and energy the universe holds compared to a critical density. If there's more than that amount, space curves inward closed. If there's less, it curves outward open. If it matches exactly, the universe is flat. To find the answer, scientists study the cosmic microwave background, the faint light left from just after the Big Bang. Its tiny ripples reveal how space bends light over immense distances. So far, the evidence suggests the universe is very close to flat, so flat that any curve is too small for us to measure today. But flat doesn't always mean infinite, and closed doesn't always mean walled in. Closed universe can be finite, yet unbounded like the surface of a globe. You can walk forever without hitting an edge, but the space still has a measurable size. Applied in 3D, it means the universe could be a self-contained bubble with no boundary. And if the universe is infinite, then there could be endless galaxies, stars, perhaps even repeating patterns, including another version of you, living a slightly different life. We can only observe a tiny fraction of all this. The rest is beyond our horizon, too far for light to ever reach us. Even so, the shape of the universe also hints at its fate. A closed universe could eventually stop expanding and collapse in a big crunch. An open or flat one could keep expanding forever, thinning out into darkness. With dark energy speeding things up, collapse seems unlikely. No matter the outcome, we're part of this structure. Our atoms, our light, even our thoughts are bound to the geometry of space itself. Whether the universe is flat, curved like a bubble, or open like a saddle, we're woven into its fabric, tiny creatures looking up, trying to imagine the shape of everything from the inside out. Curved space can feel strange, but it follows its own simple rules. On a flat surface like paper, triangles always add up to 180. Parallel lines never meet, and walking straight means you never loop back. But on a sphere like Earth's geometry changes, triangles can add up to more than 180 parallel lines eventually meet at the poles. And if you keep walking straight, you'll circle back to where you started. Now scale that idea up. Imagine the universe itself shaped in a similar way, not just curving in 2D like the surface of a balloon, but in 3D space, maybe even higher dimensions we can't picture. Galaxies are like dots on that balloon. As the balloon expands, the dots move apart, not because they're sliding, but because the space between them is stretching. That's what we mean when we say the universe is expanding. This also explains why there's no center. On a balloon, every spot moves away from every other spot equally. The same happens in the cosmos. Expansion is everywhere at once. You could travel forever without hitting an edge, looping back eventually if the universe is curved and finite, yet without boundaries. Einstein's general relativity showed that space isn't a static backdrop. It bends and warps depending on matter and energy. Mass tells space how to curve, and curved space tells matter how to move. Light, too, follows these curves. Instead of straight lines, it travels along the shortest possible path, called a geodesic. That's why massive objects bend light, creating effects like gravitational lensing, where galaxies and black holes act like cosmic magnifying glasses. Back to our balloon. As it inflates, galaxies move apart, but the galaxies themselves don't grow. Our Milky Way, solar system, and Earth aren't stretching. Expansion only works on the vast scales between galaxy clusters. And what's driving this? It's dark energy, a mysterious force built into space itself, causing expansion to speed up like a balloon that inflates faster with every breath. We don't yet know what dark energy is, but we see its impact in the way galaxies drift and in patterns of ancient light. So what about infinity? Is the universe endless? Right now, measurements show space is extremely close to flat, which suggests it could be infinite or at least much larger than the part we can observe. Our observable universe is about 93 billion light-years across. Beyond that, it might go on without limit. Here's the catch. We can't prove infinity. We can only see so far, like standing on a beach and spotting only sand, not knowing if the shore ends or stretches across a whole continent. Infinity isn't a number, it's a concept. We search for clues. Does space curve back on itself? Does it stop? Or does it just keep going? So far, no sign of an edge. If space is truly infinite, then stars, planets, and galaxies might also be infinite in number. That would mean endless possibilities, even other versions of us. In an infinite cosmos, patterns repeat. Somewhere there could be another you, living a life that's slightly different, or almost identical. These versions are unreachable, though their light will never reach us. Not even if we waited longer than the universe's age multiplied by every grain of sand on Earth. Infinity changes how we see the universe. Instead of a very large space, it becomes a boundless one, with no edge, no wall, just more universe forever. Scientists are careful about calling the universe infinite. We only have a limited view, and it's possible that space, while huge, might still be finite. It could curve back on itself in ways we can't yet measure, or take on a shape far more unusual than we imagine. Time is another piece of the puzzle. The universe might stretch endlessly in space, but it clearly had a beginning, the Big Bang. Even if it's infinite in size, it hasn't always existed in its current form. Infinity itself is hard for us to grasp. In everyday life, almost everything has limits. Our time, our energy, even the number of cookies in a jar. Infinity removes those limits. That can be thrilling or unsettling. Philosophers like Aristotle once rejected the idea, saying the universe had to be finite. And even now, experts debate whether infinity truly exists in nature or only in mathematics. But whether space is infinite or not, thinking about it has value. It reminds us of our smallness, fuels science, and sparks imagination. When you look up at the stars, you're glimpsing only a tiny part of something incredibly vast. Now, about edges. We grow up surrounded by boundaries, fences, walls, boxes, so it's natural to picture the universe as having one, two. But it doesn't need an edge. Think of Earth. If you walk straight in any direction, you'll eventually loop back to your starting point. There's no wall or end of Earth sign. The surface is finite, but it has no edge. Cosmologists apply that same idea to three-dimensional space. It's called a finite, unbounded space. Picture a donut-shaped surface. Or think of old video games like Pac-Man, where leaving one side of the screen makes you reappear on the other. Space might behave that way, looping back on itself without walls or borders. If the universe had a true edge, it would raise impossible questions. What lies beyond it? More space? Nothing at all? By contrast, a universe without edges avoids those contradictions, simply exists, stretching or looping without boundaries. Even if space has no edge, time does. Our universe began about 13.8 billion years ago. It's the Big Bang. Asking what came before is like asking what's north of the North Pole. The question breaks down. This brings us to one of the most important clues about the early universe, the cosmic microwave background CMB, around 380,000 years after the Big Bang. The universe cooled enough for protons and electrons to form hydrogen. Suddenly, light could travel freely for the first time. That light is still with us today, stretched into faint microwave radiation. We discovered it by accident in the 1960s, when Arno Penzias and Robert Wilson picked up a persistent hiss with their radio antenna. After ruling out equipment issues and even removing pigeons nesting inside, they realized they had stumbled onto the afterglow of the Big Bang. Since then, satellites like COBE, WMAP, and Planck have mapped the CMB in detail. Though it looks nearly uniform, it has tiny temperature ripples, just millionths of a degree. Those small differences were the seeds of galaxies, stars, and eventually us. The CMB is more than just leftover light. It's a blueprint of the early universe, showing us how matter was distributed and offering clues about its shape and origins. Even today, it's still whispering across space, a faint reminder of the universe's first light. If space were curved like a sphere, saddle-shaped, or perfectly flat, light would travel in slightly different ways. By studying the patterns in the cosmic microwave background, CMB, scientists can measure how space is shaped. So far, all evidence points to a universe that is flat, at least in the part we can observe. The CMB is more than just faint radiation. It's a record of the early universe. Think of it as ancient light carrying information about the shape, size, and contents of everything. Though invisible to our eyes, it's still around us today. With the right instruments, you would detect it everywhere as a gentle, uniform background signal. It's the universe's oldest snapshot, a baby photo taken more than 13 billion years ago, long before galaxies and stars existed. This light continues to reach us after surviving the birth and death of countless stars and traveling unimaginable distances. Unlike many mysteries in cosmology, the CMB is something we can actually measure and map. It shows us that the story of the universe isn't hidden at the edges of space, but written in the glow that fills it. 8. But the question of edges never goes away. Could the universe stop somewhere? Well, scientists think not. Yet there are fascinating theories that explore the possibility. One idea from brain cosmology suggests that our three-dimensional universe is like a membrane floating inside a higher dimensional space. All forces except gravity are trapped on this brain. Gravity being weaker might leak into those extra dimensions. If that's true, then the universe could have boundaries in higher dimensions, even if from our perspective it feels endless. Another idea comes from early cosmic history: domain walls. When the universe cooled after the Big Bang, different regions may have settled into slightly different physical laws. The borders between them could have created massive walls across space. Most theories suggest these walls quickly faded, but some speculate they could still exist. Dividing one region of the universe from another, crossing one might mean entering a universe where the laws of physics are just a little different. There's also the bubble universe scenario. During cosmic inflation, space may have formed bubbles, each becoming its own universe with unique laws and constants. This eternal inflation leads to a multiverse, countless bubble universes expanding separately. If true, our universe has an edge, but only where our bubble meets the larger inflationary space, far beyond our reach. In 1949, Kurt Gödel, famous for his work in mathematics, proposed a different model: a rotating universe. In his solution to Einstein's equations, the entire cosmos turns as one, twisting space and time together. This strange rotation would make time loops possible, in theory, allowing travel into the past. Our universe doesn't match Gödel's model, but it shows how the equations of physics allow worlds stranger than we can imagine. Another striking idea is the holographic principle. It suggests that everything happening in our three-dimensional universe may be encoded on a distant two-dimensional surface, similar to how a flat hologram holds a 3D image. In this case, the edge of the universe isn't a wall, but a boundary of information. The deeper lesson in all these theories is that edges may not look like walls or barriers at all. They could exist in higher dimensions, in the physics of the early universe, or even in the way information itself is stored. Or perhaps there are no edges, only limits to what we can observe or calculate. We naturally expect boundaries because everything in our daily lives has them. But the universe may play by different rules. It could loop back on itself, stretch out infinitely, or exist as part of a higher dimensional reality. Or maybe it's something beyond anything we've thought of yet. And if this universe is only one bubble among many, that brings us to the multiverse hypothesis. The idea that there could be countless universes, each with its own version of physics, particles, and timelines. Maybe even infinitely many. Imagine universes where gravity works sideways, cats stroll across ceilings, or your teenage haircut actually looked good. As fun as that sounds, let's be clear. There's no direct proof that other universes exist. We haven't seen them, measured them, or bumped into them. The multiverse is an idea born from physics, not a proven fact. Still, it's not as far-fetched as it might seem. Scientists have proposed several kinds of multiverses, each built on different theories. The first is the cosmic or bubble multiverse. After the Big Bang, space expanded at incredible speed, a process called inflation. Many physicists believe inflation wasn't even, but patchy, forming countless bubbles of space. Each bubble could be a separate universe with its own rules of physics. Some might not allow matter at all, while others could have entirely different forces or particles. We live in one bubble where conditions happen to be just right for stars, planets, and life. Then there's the quantum multiverse, based on the many worlds interpretation of quantum mechanics. It suggests that whenever something can happen in more than one way, all outcomes do occur, each in a separate branch of reality. In one universe you pressed snooze, in another you made pancakes, and in yet another you invented teleportation. Every choice and chance creates a new branch. It's a serious theory, but like bubble universes, we can't currently test it. A third idea is the mathematical multiverse, suggested by cosmologist Max Tegmark. It claims that any structure that's mathematically possible actually exists as a universe. That would mean not only other physical laws, but even other logics. Universes where numbers and constants themselves are different. Bold, yes. Testable? Probably not. Critics point out that if other universes can't be reached or measured, how can we call them science? Some worry the multiverse drifts too far from testable physics. Others argue it helps explain why our universe has the laws it does. If countless universes exist, it makes sense we re-in one where life is possible, much like rolling dice until the numbers finally land right. Some scientists even wonder if traces of other universes could show up in the cosmic microwave background as patterns left from bubble collisions. So far, no clear evidence has appeared, but researchers keep looking. Whether or not other universes exist, the idea pushes us to think bigger. It reminds us that reality could be far stranger than what we see. And even if this is the only universe, our curiosity has already taken us across galaxies in thought. That's no small thing, which brings us back to the big question. Where does space stop? We've learned that space isn't like a box with walls. It stretches, curves, and expands. It may be finite, yet unbounded, or possibly infinite. There is a limit to what we can observe, a cosmic horizon. But we don't know what lies beyond it. Space could go on forever, fold back on itself, or exist as one bubble among many. Or perhaps the multiverse is just a poetic idea. What we do know is that space is full of structure, light, and energy. It carries the glow of the Big Bang and has no clear center or edge. The unanswered questions aren't failures. They're the heart of science. The cosmos may never stop, not just in size, but in mystery. Maybe that's the point. Space is an open invitation to wonder, to ask questions, and to dream. So tonight, as you think about galaxies and horizons, maybe you'll find peace in the asking, because curiosity itself is its own kind of cosmic magic.